Hello. In this lecture, we will go over deep learning and we will cover some basic notions in it and we will see an example. So how is deep learning different from the rest of the methods that we have seen, um, other machine learning methods? How is it different? Well, the difference is that there is a emphasis on learning successive layers of increasingly meaningful representation. So we have an input image, an image uh, that goes through a first layer. This first layer, you can think of a function being applied to this layer, to this input image, and then there's another layer, another function. Each of these layers stands for a function, and here we have four layers, four functions are successively applied, and each of them captures um, some aspect of this data that we are interested. And then at the end, we have this output layer, which combines all these outputs, and then it is able to read this digit 0, 1, 2, 3 to 9. And here you can see what I mean by learning successive layers. The first layer pays attention to these patterns, the second layer to these patterns, the third layer to these patterns at very specific locations. And then once they're all combined, they will lead to a final output. Okay, so um, the deep here isn't really referring to anything conceptually deep. It's more about depth. It's more about layered representations, about hierarchical representation. And each of these layers stands for a layer in this hierarchical representation learning. Okay. So you can think of a linear regression as being a single layer neural network. You have just one layer and you have these weights, which for us in linear regression means the coefficients, and we have this input and we calculate an inner product with the weights, and then we have the response. Now imagine that you do this inner product and then you also apply in nonlinearity. And you do many of them, so you have many outputs, and then you have these many outputs, and then you calculate again the inner product with the weights, and then another nonlinearity, and then you combine them and you have a prediction. So you have these layers, which within them might each of them have a linear regression followed by some nonlinearity. So each layer is at least as complicated as a linear regression or a logistic regression. It can be even more complicated. Okay, and so essentially what a layer does to its input data is stored in the layer's weights, uh, or it's parameterized by the weights. Okay, so there are many parameters here in a network. A neural network is over parameterized. It's very flexible, and that's why it's able to capture um, non-linearities or very complicated data structures. So how do we determine these weights? How are these weights learned? So we need to measure how far the output, this prediction, is from the true observations, the true target. So you have the predictions. So every neural network, whenever you're training it, you also have a loss function, something we are very familiar with. or objective function, and then we like to adjust these weights so that the predictions is as close as possible to the true targets. Now the major trick in deep learning is to use this discrepancy between the prediction and the target, okay, uh, in a smart, intelligent way to adjust these weights so that the predictions become as close as possible to the targets, and then they do that iteratively. So uh, the score here is used as a feedback signal to adjust the values of the weights just a little bit in a way that will lower the loss, this loss. So in a way that will lead to the prediction to be closer to the true target. And this adjustment of the weights is the job of what we will later know to be the optimizer. Okay, and the way it's done, it's through the back propagation algorithm. It's a central algorithm in deep learning, and it's very technical, but essentially it allows us to adjust these weights in a computationally efficient manner, and that's the major accomplishment here. So back propagation. Well, in the beginning, the weights are they're random. They're randomly assigned to whatever, but in each iteration, as the network goes through the data and compares the predictions with the true target and uses this discrepancy between the prediction and the true target as a signal to adjust weights, then the network becomes better and better. So this is maybe a complete weight. So this loss function gives signal to the optimizer. The optimizer changes the weights, not just this weight, also this weight. So there should be also an arrow to this one, just a little bit, and then when it's done for many iterations, then the network will fit the data better and better. Okay, so let's just go over these optimization algorithms, the different ones. This is a great review paper published in 2017 if you're interested. And so the major um, thing here is that you have this objective function, j of theta, which in linear regression was this mean squared error. In classification, it can be cross entropy. But essentially, it's a loss function, the loss function that we just saw a second ago. And then we have these parameters theta, which stand for all the weights involved in this neural network. Okay, and the way to optimize it is to take the gradient with respect to the parameters, and then we have this learning rate, and update this parameter, so calculate this gradient for all the data, and then update this parameter iteratively until we reach the minimum. Okay. Now here's a problem. We have to use all the data, and all the data might be too big for us, and therefore people have come up with stochastic gradient descent that instead of using all the data to construct the gradient, it uses one data point or a small number of data points at a time. So in each iteration, it randomly picks a data point, xi and yi, and then sees how well the network is predicting this data point. And then if it's not predicting well, then it updates the parameter, the weights of the network just a little bit, so it's less bad. So it's a little bit better. So you see that stochastic gradient descent fluctuates a lot. Here we have the iterations, and here you have the cost function. So you see as the iterations improve, the cost function, the measure of how well the network fits the data, overall it's getting better, but sometimes we have these fluctuations which takes us up. So we would like to avoid these fluctuations and perturbations. We want something that steadily decreases. So mini batch gradient descent does something in between. So instead of looking at all the data in each iteration, which can take forever, or one data point at a time, it looks at mini batches. And for every mini batch of n training examples, so it splits the data in these batches, and it says, okay, from data point I to I plus n, use all that data and calculate the cost function, take the gradient, and then update the weights a little bit so that for that batch, the network is doing slightly better. Okay? So that's mini batch gradient descent. So stochastic gradient descent will iterate until it reaches the minimum here, hopefully. But it can be slow, this iteration, and we like this to be a little bit faster. You can see here, this is the steps are more in the direction of the minimum, and that's done with something that's known to be a momentum. And momentum takes into account the previous steps rather than just the last step. And the way it works is that it not only looks at the gradient, it looks at the rate it has changed in the previous step and has a memory of it. So it will just integrate the previous steps into the next step as opposed to only the last step. There are many variants of adding momentum, and I won't go over them. I will just briefly tell you one that we will use in this class, RMS prop. And the good thing about this, it has an adaptive learning rate, and it also has some momentum. And this is the formula. So you see the previous steps, and not only the last step, but also not only the last step, but also the previous steps are integrated here, and it seems to work well in practice. So I mean, this might not be very informative what I told you, because there are a lot of details in this image, but let me just tell you this. RMS prop allows us to have an adaptive learning rate. Essentially, this coefficient here changes depending on what's the G here is the gradient, and it also has momentum. So the landscape of neural nets is highly nonlinear. They don't have one local minima, and it's important. These are saddle points. This is a saddle point. It's important not to get stuck. The stochastic gradient descent would get stuck here, where we see the RMS prop would quickly get away and would just slide down, and that's exactly what we want. And other deltas and other method is doing also a great job, but saddle points can be problems, and we want to avoid them as much as possible, and that's why we want optimization methods that don't get stuck into saddle points. So here's again a representation of a feed-forward neural net. Here we have 4 features. These 4 features, this is the first layer, the input layer. Here we have 1 hidden layer, and then we have 1 output layer. And these will just get distributed to all these nodes. So you can think of each of these lines to be a weight. So x1, x2, x3, x4 are transformed through an inner product with some weight, and they go into this node, and then this node applies a function. It can be a linear function, it can be a nonlinear function. And typically it's nonlinear. It's nonlinear, and then and then each of them will have an output on their own, and then in the end, in the output layer, if you're doing regression, these outputs are again going through a linear function, and then typically the output layer is just a simple linear function. And the whole thing is, how can we adjust these weights so that this output is as close as possible to the data we have. And here you can have, you can have as many layers as you want. And in a lot of cases, these layers represent different hierarchies of information in the data. Okay, and you can have more. The output layer doesn't have to be one node; it can be many nodes, and that happens when you have a classification problem with more than one category. So here is again another way of looking at it. You have an input layer. The input layer has typically the number of nodes in the input layer are equal to the number of features you have. And then you have the hidden layers, and then you have the output layer. Now, each of these nodes, so what is each of these nodes? What is each of these? Each of these nodes is one of this. So I'm here zooming in into one of these nodes, and each node receives input from the layer before it, right? So imagine you have these inputs. One here is just the intercept, and then you have x1 to xm. Imagine you have m features, but this can also be here. So 1, 2, 3, 4 inputs can be can be 4. So each input is multiplied by a weight. Then there is a summation going on, and then it goes through some non-linearity. It can be a sigmoid, it can be linear, it can be rectified linear, and each of them will lead to different networks with different properties. Okay. The typical functions are linear. They can be a rectified linear function, which is linear for positive numbers and 0 for non-positive numbers. So for negative numbers, it's 0. It can be a sigmoid. It can be a softmax. These are the typical. These two are typically used for these are for classification. And this is how you can define a network in R. What is this saying? It's saying that the input layer takes P as P, which is the number of features in. The nonlinearity is ReLU, rectified linear unit, and the units are 128. So this is P, and then this will be 128. Okay, so you have the input layer, and then you have these 128 ones, and their nonlinearity is rectified linear unit. And then after 128, you have 64. And the 64 is again rectified linear units. And then the output of those goes into 10 units, where each of the 10 units has a softmax output function. So this is useful if you wanted to solve a classification problem with 10 categories, which is, one example is reading handwritten digits. Okay. Now this is just to define the architecture of the network. We also need to define the optimizer. Recall here we first defined the architecture of the network. Now we need to define what is the loss function for us, and then what is the optimizer. So once we define these two, then we know then the program knows how to adjust the weights. Okay, and that's how it's done. So if you're doing classification, the typical loss is categorical cross entropy. Those who, I mean, that's cross entropy. So it's a measure, it's a way to measure the performance of classification algorithms. And the optimizer is RMS prop, and RMS prop is I mean, it's beyond the scope for me to go into the details, but it's one of these ways to update this theta here stands for the weights, all the weights of the network. We just use that theta, and this is how it's done. And so when we say RMS prop, this is the scheme used. Okay. And the metric is here accuracy, and the metric, let's just skip the metric for now. I will talk about it later. The metric is used for us here to monitor how the network is improving over iterations. But we are not doing classification now, so this is an example of classification. We will see a regression example later. Okay, so let's look at an example. The major library that we need to use for deep learning in R is Keras, and the data set I will use is a Boston data set. Okay. Okay. So this data is from a given Boston suburb. So median price of homes in a given Boston suburb in the 70s. Um, we have crime rate, local property tax rate, and so on. And it has 506 um, total data points, and 404 of them are training, and 102 are test data. Okay, so this is the train data. What's the dimensionality of train? Uh, so we have 13 features, 404 observation, 102 test observations, and the targets, these are the targets. It's okay, more or less unimodal. Um, you don't need any transformation. If your data is very right skewed or left skewed, applying a log is useful. Okay, but here we don't need it. Here, what we will do is we want to pre-process the data. And one thing that can become a problem is to feed into a neural network values that take widely different ranges, okay? And since the predictors are different scales, um, we would like to change the scale so that they all are more or less in the same range. The network might be able to automatically adapt to the heterogeneity in the data, but it makes definitely learning more difficult. So it can lead to numerical instability, slow learning rates. So in general, it's safer to do some sort of feature-wise normalization. So each feature in the input data, we subtract the mean and we divide it by the standard deviation. So the feature is centered around 0 and has a unit standard deviation. And that's easily done with the scale function in R. We scale the training data, we scale the test data. We just pay attention here that we scale the test data with the mean and STD that we obtained from the train data. Okay, and the reason is that because we don't want to use the test data twice. We want to leave the test data for testing. Okay. Now here in this function, we build the model. Okay. So we have for input layer. What is this? Sorry. .13. So the input shape is just 13 nodes, and that goes into so we have essentially a small network. We have one input layer, we have two hidden layer each with 64 units, and the activation function is rectified linear. Okay, and this is already a very highly for the size of the data we have. This is big, but if you have more data, you can make deeper networks. So the more layers you add, the capacity of the network will increase, and the network will become more flexible. But since fitting larger networks will take longer, and since the data that we have is not big relatively, that's why I think this size is okay. Okay, and then the network ends with a final layer with a single unit that has no activation. So when you don't when you do not specify the activation, it's just a linear function. So the last layer is just a linear function, but the previous layers are doing some sort of automatic feature engineering. They're just trying to find what are the non-linear features in the data that are meaningful. And then the last layer, then it's just a linear function. And since the last layer is linear, and since the responses are numerical, then we are okay. We could have had something like rectified linear here. We could have done that. That would be fine. We could have used sigmoid, which wouldn't have been fine because sigmoid limits the output to be between 0 and 1. So you have to be a little bit careful. We talked about the optimizer, the loss function, and the metric. The metric here is to give us how the measure in which the performance on the test set is presented is going to be a mean absolute value. The measure with respect which the optimizer is going to adjust the weights is the mean squared error. Okay, and the units are in $1,000. So a mean absolute error of 0.5 means $500. Okay. Now, we would like to evaluate the network while we keep adjusting the parameters. And the parameters we have is the number of epochs. I will talk about that during later what epoch is, but actually it's here. Let me just say. Epoch describes the number of times the algorithm sees the entire data set. So each time the algorithm has seen all the samples in the data, an epoch has completed. Remember, we use the method that we are using is a stochastic gradient descent method that scans the data and adjusts the weights. And here we are not adjusting the weights until we find the local minimum. We just adjust the weights as many times as we tell it. And here it's 100. So 100 times we go through the data, and 100 times the optimizer sees all the data. Okay. And here we want to use k-fold cross validation to evaluate the network. Okay. Here we are shuffling the data. This is a really nice line. What it does is it assigns every data point to a fold. We say k folds. So you have the folds, and then we have the indices. And this means that how many data points we have? We have 4, so length of indices is 404, length of folds is 404, and that means that let's say we want to indices 1 to 10 and folds 1 to 10. That means that data point 385 is assigned to fold 4, data point 216 is assigned to fold 3, and so on. Then we repeat this k times. Here it's announced that we are processing fold number 1, 2, 3 to 4. And then we are finding the indices of data points which belong to fold I. We put it here. Using these indices, we take part of a training data, becomes a validation data. We take the validation targets. Okay, so this will be the kth fold validation, and then the rest of it will become partial training data, partial training targets. We build the model and then we fit it. Okay, build model is this function which we are going to use repeatedly. So instead of just having all these lines here, we just use this line. We already defined what we want to do, and then we fit it. We fit the network to the partial training data and targets. We say we specify the epochs. Batch size, we talked about it. Batch size is the number of data points used in each iteration of the stochastic gradient method. And then once it's fit, we evaluate it on the target and the validation data, and we restore the mean absolute errors. Okay. So here we have the scores, and we see that for fold 1, the predictions were this much off, mean absolute error. For fold 2, this much off. For fold 3, this much off. For fold 4, this. I already ran it. It takes some time, so just to save time, I just show you the results. And then we take the mean. So it's $2,469. Sorry, $2,406 off on average. Now we want to play a little bit with the iterations. We want to see if we increase the number of epochs, if anything will change. And therefore, we run this again. We also want to keep a record of how well the model does at each epoch. So we want to know as the number how as we increase the number of epochs, how as the optimizer goes through the data more and more, how the performance changes, and therefore we are modifying the training loop to save the per epoch validation score, which is done here. Okay, and then the history has a metric, and we care about the mean absolute error, so we put it here, and then we bind them below each other. Here we are averaging them. Okay, so that is seven, 4, 5. So this is for each of the folds, and we have 500 epochs. We want averaged over the 4 folds, and that's what we are doing here. And then we are plotting it. We could have just, we are smoothing it, so let's just see without smoothing first. Okay, I don't know why it's not doing. Let's just skip the smoothing. Okay, so we see that actually around after 50 epochs, the model stops improving. Okay, so we don't really need to go up to 500. But this is one of the ways to tune the parameters. Okay, so let's try something a little bit different. Let's try 50 epochs and batch size, the number of data points used as 10. And let's just run this. Okay. So we are off this much. The mean absolute error is 2,600. And yeah. So this is how you can fit a network. This is one of the major things. The number of epochs is one of the things you can play with. We did with batch size 1. So with what we did here was with batch size 1. So I just want to see if we do 50 with batch size 1, what do we get? 2.4. So we will reduce the. So again, this is the loss for fitting the data. This is the evaluation um, on test data. So actually, sorry, this is the, both of them are for the test data, but this is what we care most, mean absolute error. So it's around 2,400 away, and this is a small number, this is a large number, depends on the range of the response. Um, range is in the 20-30, so it's like 10% off. Okay, so how are deep neural networks different from recurrent neural networks? How are they able to capture some nonlinearities and complicated relationships? This is the subject of my what will come next. Okay. Okay. So deep forward networks, the goal is to approximate some function f star. And unlike linear regression, where we make the assumption that that function can be captured in a way that the response is associated with the features in a linear fashion, we do not make any assumption here, and neural networks are flexible enough to more or less capture any nonlinear relationship. So what makes them feed forward? There are no feedback connections. As I talked before, we have the first layer, then we have the second layer. This is a third layer, and then this is the last one. And these are all just going through without any feedback connections. Whereas a recurrent neural network, the nodes are connected. There is no hierarchy going on, and these are just connected. Any node can be connected to anything. So we do not. Recurrent neural networks have a bigger. Well, just forget about them. It's hard to fit them, and when people talk about neural networks in machine learning, um, it's deep, deep, deep neural nets are feed forward, and what makes them easier to fit, what makes it easy for us to adjust the weights between the nodes so that the response is close to the observed response, is the feed forward uh, nature and the lack of feedback connection which exists here. Okay, so the take-home message is that recurrent neural networks have feedback connections. There is no hierarchy of representation, whereas deep neural networks, or also known as feed-forward networks, there are no feedback connections, and each layer sometimes represents a hierarchy of representation in the data. Okay, so the depth of a network is the overall length of the chain. How many layers do we have? The output layer is the final layer, and let's just compare it to a linear model. A linear model just applies a linear relationship to x, but when we have a deep forward network, in the last layer, in the last node, as we saw in the example, if we don't specify it, it's a linear function. Okay, so instead of applying a linear function to x, it's applied to a transformed version of x, where x is a phi is phi of x, where phi is a nonlinear transformation. But how do we choose the mapping? In the past, we talked about nonlinearities such as squaring x or interactions. So these are all manual, right? We can manually add interactions, we can manually add non-linearities, but in a feed-forward neural net, this non-linearity is learned from the data. Okay, so to be concrete, the strategy is to learn phi. So we have this y, which is depends on our input, uh, some theta and some beta. This theta, and then this is this linear relationship between beta and a transformed version of phi. Okay, x, a transformed version of x, and this transformation depends on these weights, um, which are the parameters um, that we use to learn. So these are the weights. These are the weights inside the network, and this is the last layer. And we want to adjust both theta and beta such that y is as close as possible to the responses. Let's look at an example. Imagine we want to learn XOR. XOR means exclusive OR. And this is a function. We have two features. Exclusive OR means that if x1 is 0, x2 is 0, the response is 0. If either of x1 or x2 are 1, the response is 1, except for when both are 1. That's why it's called exclusive OR. So it's just only one of the x's can be non-zero for the response to be 1. And we want to learn this. So we have these 4 points. This is x21. This point is x21, x10. This point is x11, x20. This is x1 and x2 both 1, and this is x1 and x2 both 0. So we want to fit a function to learn this relationship. And if we use the mean squared error, we have 4 data points. This is our f star. And if we use a linear function, then if you use a linear function here and you fit it, you take the derivative, you set it to 0, what you get is that beta hat is 0 and the intercept is 1. So the linear model simply outputs 0.5 everywhere. Which is terrible. Just terrible. Now imagine we want to have a simple feed-forward network with one hidden layer. This is our first layer, this is our hidden layer, this is our output layer. Okay, and so x1 goes here, x2 goes here. They have 2 weights. They're added, go through this function, gets it out. The same here, gets it out. Then here we have a linear function. So we can represent this in a simpler form by simply calling this W a weight matrix that takes the feature vector, applies the weight, then goes through this edge, which is summarizing these two, and then goes to y. Okay. So h is a vector of hidden units. This is our first function. This first function is applied to x. This first function has this weight matrix and the intercept. And then finally, h is being used as an input for the second layer, for the output layer, which is a linear regression model applied to h rather than x. So we have two functions chained together. One that takes x, and then we have the weights. It gives us h, and then h goes through this second function, and we get the response. Now the second function is a linear function, but if we want to show it, we have essentially one function here, one function here. They are inside of each other, so we have two chain functions. Okay. What should f1 be? f2, you say f2, the last layer is linear. If we also choose f1 as linear, then the whole thing will be linear and we're just stuck where we were. So we have to have some non-linearity. So what we do is we use a linear function inside, but g, let it be a rectified linear unit, or RELU, which is the max. It's taking the max between 0 and what's inside. So rectified linear is 0 for negative z, and it's just z for positive. The complete network will be beta transpose f1x beta 0, where f1x is just w transpose z plus c, passing through this non-linearity, and then this becomes our new feature vector, essentially. Beta transpose, and G is rectified linear, so max of 0, W transpose Z plus C, and then we have the, sorry, this is beta 0. This is supposed to be beta 0, this is supposed to be beta 0. B here is beta 0. Now, how we find these, it's part of the optimization algorithm, which I don't go into, but I just want to show you that by having an appropriate W, we are able to capture the function we want. So let's say W is 1, 1, 1, 1, meaning that H1, inside H1, we are just adding x1 and x2, and here we are also adding x1 and x2. And then we have the intercept, which we add 0 to 1, and then negative to 1. And then imagine the beta is 1 and negative 2, with the intercept here being 0. So these are our four observations we have: 0, 0, 0, 1, 1, 0, 1, 1. If they are applied to W, W applied to them, you have 0, 0, 0 becomes 0, 0, 0, 1 becomes 1, 1, 1, 0 becomes 1, 1, 1, 1 becomes 2, 2. And then we add the bias, which is C. So we subtract this as a row vector, so we have 0, negative 1, then we have 1, 0, 1, 0, and then we have 2, 1. And then we apply H, which is the rectify linear, to each of these terms. So the first column, which is everything that's positive, will remain the same, just the negative 1 becomes 0. and then the inner product each row with 1 and -2, and then we get 0, 1, 1, 0. So this 0. So essentially the input to the network is 0, 0, the output is 0. The input to the network is 0, 1, the output is 1. The input to the network is 1, 0, the output is 1. The input to the network is 1, 1, the output is 0. So we see that just by having this 2 layers, or actually 3 layers, but just one hidden layer, where the hidden layer has a rectified non-linearity, this network is capture a relationship that a linear model would not be able to capture. So there's a lot more, obviously, to talk. We can talk 2 semesters about deep neural nets, but I think this is a good introduction. And we have seen in our example, you are introduced to the main characters in this story. You know how to adjust them, play with them. You know how to measure the performance, how to fit it. And the big questions here is how to choose the architectures, how many hidden layers, how many nodes in each layer, which optimizer to use, which nonlinearity to use. So there are some rule of thumbs. A lot of them are domain specific, and the theory is lacking behind, and for good reason, because as you saw for the linear regression model, um, doing the math, we could calculate everything, but there were so many steps. Now imagine uh, in a neural net, essentially each node is like a linear model and then a nonlinear function after it. So it's very complicated, and that's why it's hard to say anything um, concrete. And again, there are some, the best thing, essentially to know the answer to many of these questions, you should ask somebody who has been playing with neural nets in their daily work in that specific domain that you are interested. So if it's vision, then there are some other practices. If it's about text, there are some other practices, and the theory is catching up, but we are far behind. And I don't think the theory will lead to anything. Um, well, just I'll take that back. I'm just saying this is very complicated to study theoretically, so a lot of it is experience based. Okay, thank you.